Hello and welcome back on this sunny Saturday morning. We're going to work on section 4.4, optimization problems, one of my favorite sections. So we are going to put that notion of minimum and maximum to good use now. Applied problems, right? So to illustrate what this all has to do with anything, say we want to maximize xy given x plus y is 10, let's say. So you are looking for two numbers, x and y, which when multiplied will give you a maximum product x times y. Now you can, if you just consider integers, right, you can quickly do that on the side. 1 times 10 is 10. 1 times 9 would be 9, because 1 plus 9 is 10. And then 2 times 8 is 16. And then 3 times 7 is 21. You see how it's rising as I'm picking different numbers that add up to 10. 4 times 6 is going to give us what? Very good. And then if they are the same number, 5 times 5 gives us 25. And then we go 6 times 4. Well, we're getting now the same numbers just backwards, so we don't have to actually do all of these. And by inspection, we were able to determine that if x is actually equal to y, we are going to get the maximum product. So we were looking for the maximum product as these numbers were forced to add to 10. So we are going to call this equation over here objective equation. That's what you're trying to do, to maximize the product. And this equation is constrained, because that's the constraint. X plus y must be 10, right? So that's something that is called the constraint equation. And the entire section is you reading word problems and coming up with these two equations, the objective equation and the constraint equation, and you put them together. Now let's see how we can solve this using calculus rather than this guess and check method. So what do? We go and say that we want x times y to be max possible, and we want also to have x plus y equals to 10. Now we know that if we are to differentiate the first equation, right, we will get a max. But the problem is it has two variables, x and y. So what I'm going to do is I'm going to solve here for y and plug it in. So now it becomes x, 10 minus x is equal to some unknown maximum. We know it's 25, but we're just ignoring that for now. We distribute, and then we know how to find max. We differentiate. Once you differentiate, you get 10 minus 2x is equal to 0. I'm just going to say max is some unknown number, and we know what's happening when you're taking the derivative of a number, of a constant. It goes to 0. Now you should also at this point connect that idea of first derivative equal to 0, which is how we find min and max. So it all kind of collapses here in this statement. You have a function, and you differentiate that function. When you differentiate a function, you set that function equal to 0 to find min and max. Well, if that function was already equal to some maximum number, then when you differentiate that number, it becomes 0. So you see, you can remember either way, but they're both equivalent. Whether you say derivative, set derivative equal to 0, or you understand that whatever this magic number is, we know what it is. Whatever this magic number is, its derivative is 0. So now we solve this equation and we get x equals to 5 right away. Once you have x, plug it back to find y, and we're done. So solving this equation, we have 2x equals 10, x equals 5, from where y equals 5, and we found the answers using calculus rather than inspection up there, like trial and error method. Cool, right? Oh, thank you. Next problem. Farmer problems. So farmer has, I don't know, 1,200 yard of fence. What is the maximum rectangular area that could be enclosed by all that fence? And I'll just abbreviate. So farmer has 1,200 yards of fence. What's the largest possible area that can be enclosed with those 1,200 yards fence? You draw the picture of a rectangle with x and a y. So whatever the black line is, that's the perimeter, that's where the fence goes. So you know that the perimeter equation is your constraint equation because that's what you have. You have to use all 1,200 yard of fence around the perimeter of the rectangle. So this should be common sense, I hope, that the perimeter equation is the one of the equations. And now we want to know the area. What's the area equation? xy, and we want to maximize that because what happened? All good?
Yeah, no, we got it right. So.
Oh, you're just happy. You got this right. Awesome. So guys, there they are. I have the constraint equation on top, and I have the objective equation on the bottom. I will simplify this equation into x plus y equals to 600 because I can divide by 2 everywhere to lessen the numbers. Again, solve for y, which is 600 minus x, and then plug in. This is what you will always have, this constraint equation, and the constraint equation will always be the one that will reduce the number of variables in the first one from 2 down to 1. So now x times 600 minus x equals to some maximum that we don't know. 60x minus x squared is max. We are going to differentiate now. So the derivative is 60 minus 2x is equal to 0. Why did I put 60 there? Should be 600. So 2x is equal to 600. X is equal to 300. And in this case, y is also 300. So the largest area that can be enclosed with 1200 feet is a square, 300 by 300. So up there we got 5 by 5, and this one is 300 by 300. Looks like square all the time, right? Yes? Well, we can write the sentence. Square, 300 by 300. Oh yeah, you can multiply. The problem specifically asks what is the largest area. You will calculate it. It's fine. It's okay. A step further. All right, so that's the farmer. Now we're going to change it a little bit. Say there's a river. Put some salmon in it. Yeah, if the salmon goes this way, what's the... Which time of the year is it? Which, if the salmon goes this way, which way the water goes? Salmon swim upstream, right? I love that question. I ask it every single time. I get the correct answer there. It depends on the time of the year, because that salmon has to come back sometime. Right? Doesn't matter. Don't mind me. We still have 1,200 feet yard of fence. All right, go. You can do this one. What does salmon have to do with that? Absolutely nothing. That's the beauty of it. No, that's the beauty of it. There is no need to fence off that side.
Okay, alright.
Yeah.
So this is like, oh.
I'm sorry? 600 by 300 is correct answer. Very good. So it's not a square, it's not z squared anymore. It's not a square anymore because we don't have fence towards the river. Right? We only have 3 sides. So now our perimeter equation is 2y, so x plus 2y. So x plus 2y is equal to 1200. We still need xy to be a max. We can solve for x this time as 1200 minus 2y and plug in. It doesn't matter which one you solve for. We have 1200 minus 2y times y equals a max. And then we have 1200y minus 2y squared equals a max. And then we are going to differentiate that. Have 1200 minus 4y equals to 0, from where y is 300. And then eventually x is 600. So 300 by 600 yards, since they're asking for dimensions, not for area. But you can compute area as well. One more variation. Again, farmer. Let's say we have 3 bins, like this. Needs to separate stuff. I don't know, carrots, rabbits, and tigers. There you go. But you don't keep them together. Rabbits eat the carrots, right? Tigers eat the rabbits. So don't put them together.
You could just like have the tigers and the carrots in the same area, right?
Nah, I'm gonna pee on carrots.
Yeah, I'm sorry.
Just don't.
Go while they're sleeping then. Well, that's why you have the rabbits go with the carrots.
This is a very worthwhile discussion. Please go on. I shouldn't have said anything. We still have 1200 yard fence. Max area, dimensions. Let's see. Go on. While we're still young. He just did. All right, done. And then after this is just, you know, like that. That's when you run out of ideas. So we have what? 2x plus 2y plus half x plus half y equals to 1200. And you still have xy equal max. And go on. So, you know, whatever the geometry is, you have to make that perimeter take in account, you know, all of the lines. Well, too bad he left, because the next problem is the challenge for you to actually make. So next problem is the box. So you're looking at the box, and you want to figure out the box that you can make out of the given piece of paper, let's say, which would have the maximum volume. So that's what we are looking for. Now, this is the challenge question for you to try and solve at home and actually make this box. So you will take a piece of paper, put it down to a square, obviously, dimensions, and then once you have the square dimensions on it, you will calculate how much you have to cut on each corner so that when you bend the edges up, creates a box that will have no top and maximum volume. Awesome, right? So the square paper would look like this, let's say. You will cut out these edges. So those are the ones that go out. You fold here and you get the box. These will be your x's. These are your y's, obviously, because when you stand them up, they are the height of the box, the way I labeled it there. So you should be able to figure this out. Okay, let's do one of the business problems. Sound good? Make some business decisions regarding this. I don't think this should be, a large issue for you to solve because the equation over here, right? You know, times the volume of this and then the side minus these two pieces and so on. We'll figure it out. Not that bad. So let's see. I'm going to make up a problem and hopefully the numbers work out because this book doesn't have the exact problem that I would like to discuss. So let's say this is a shoreline. All right, so this side is land, this side is sea. I'm going to place a refinery here, oil refinery. So let's call this a factory. And let's say that the oil rig is right here. And we can run pipes on ground, then underwater, directly underwater. So these lines are pipes. So let's say that this is, I don't know, 6 miles. Let's say this is 4 miles. Price per mile above ground. I know. $100,000. We're talking about pipes, right? And the price per mile underwater. Oh, 200, let's say, double. So that's price of installation for the pipeline. So you can see that you have these two options, right, so far. We'll try to figure out another one. One option says just go up the shore as much as you can and then with a cheap pipe and then have the shortest possible path to cover using the expensive pipes right underwater. And then the other one says, well, if we just run it directly, right, straight through, it will be the shortest route. So the question is, which one is better? Or can we do better than this? So we can quickly compute. We don't need any calculus to compute this, right? All I need to do is to figure out what is the length of the across line, right, the hypotenuse of the triangle, and multiply by the amount of how much each pipe would cost. So it's a simple arithmetic problem, and then we're going to involve calculus and see if we can do better than that. So let's call this option 1, and let's call this one option 2. So option 1, would be 6 times 100,000 plus 4 miles times 200,000. So the cost would be 600 plus 800, $1.4 million. Okay, let's go purple, option 2. Well, we first have to figure out what's the length, right? I don't know what you guys are computing. I'm going to say 6 squared plus 4 squared. So we have 6 squared is plus 4 squared is, so root of square root of 52. So the cost for the second one is the length, which is square root of 52 times the cost for underground is 200,000. So what is that now? Square root of 52 times, you see it's going to be worse, right? What is it? 1,400,220. So we see that the option 1, right, is better. Even though you're covering 10 miles with pipes, and the one on the bottom covers just over 7. So even though it's 3 miles longer, we see that we get the better deal. But the next question is, can we do better? Can we do better than this? And hopefully we can do better than this. By running piping to some point and then go like that. That should be better. Now let's see if this is possible. So option 3. For option 3, I will have that D over there, which makes this length 6 minus D. And I also have the Pythagorean theorem for this length, which is the square root of 6 minus D squared plus 16, right? 4 squared. So now, we have our cost equation. Cost equation is going to be $100,000 times whatever D is plus $200,000 times square root of 6 minus D squared plus 16. And that needs to be minimum. So one more time, I'll try to fit everything on the page. Equation and all right. So what I'm trying to say here is that there is some unknown distance that we have to go on the land, and then the remaining under the water, and we are trying to set it so that the cost works out to be less than 1.4 mil, right? So whatever I have here, that's above ground times 100,000. And then the remaining here is the underwater. Now how do I get this? Well, I know that this is a right triangle. One leg is 6 minus B. The other leg is 4 miles. You can't change that. So here is the leg squared plus 4 squared is 16. Square root of everything is the length of this line. That's the Pythagorean theorem. C squared is equal to A squared plus B squared. Very simple. So I have that. Plug everything in. The cost equation, the price per mile times number of miles plus cost per mile underwater times the distance underwater. So all we need to do is to distribute all of this, differentiate, solve the equation for D. Once we have the value for D, we can quickly calculate the other length, and we're done. So 100,000 D plus 200,000 square root of 36 minus 2D plus D squared plus 16. So 52 minus 2D plus D squared equals a minimum. Now we're going to differentiate. Yes. I can't hear you, sir. Yes. Oh, I didn't put 12, I put 2. 12, 12, 12. It's 12D. I put it in blue now. Because 6 times 2 is 12, yeah? 6 times 2 is 12. So that's 12D, negative 12D. Cool. Time to differentiate. Don't we all love this part? Yeah, we all love this part. 100,000 plus 200,000, 1/2 of 52 minus 12D plus D squared to the negative 2, sorry, to the negative 1/2, and then times the derivative of the inside, which is 2D minus 12, equals to 0. $100,000 plus 100,000 times 2D minus 12 divided by the square root of 52 minus 12D plus D squared equal to 0. Now we know we need to move this term there, and when we divide it by, yeah, I'll do this step by step. So 100,000, 2d minus 12, 52 minus 12d plus d squared is equal to 100,000. Divide both sides by 100,000. And we get that 2d minus 12 over the square root is equal to 1. Yeah, negative. Cross multiply. 2d minus 12 is equal to negative square root of 52 minus 12d plus d squared. And we now square both sides to get rid of the square root. We are now solving equation, right? Go on. What should we do? Distribute. Well, FOIL, right? So we have 4d squared minus 1248d plus 144 is equal to, negative sign goes away, right? Because of the square. Square root goes away. So we just have 52 minus 12d plus d squared. Now what? What should we do? Like terms. So we have 3d squared, and then this goes as a plus, so minus 36d, and this goes to 92. Anyone? 90. Equal to 0. So these are not going to be nice numbers, right? What do we get? D equals. What are the numbers? No one did this? Are you at least doing it now? So I have 3.459 and D equals 9.78. 5 if you need to know the 3 decimals like above. So now observe that this is the number that it's in the range for us, right? Because remember that all the way to the top is 6 miles. So there's no way that you can get another one for 9, right, in there. So there's only one distance, d. And once you have distance d, you can plug back into. Now what this does is guarantees minimum cost. So that means that you're going to dig about 3.5 miles and put the pipes that way, and then whatever is left over goes through water. And we can again use arithmetic to show that these numbers will give us the lowest possible cost regarding all of these problems. All of these options, that's what I meant. Options in the option 1, option 2, and option 3. So option 3 is optimized, right? Option 3 is the one that shows the lowest cost. So you can go and plug D back into the equation to find how far it goes underwater, then multiply by 200,000, multiply this number by 100,000, you will see that the values should be smaller than your this one, option 1 and option 2. Good. One more problem before we hit the break? Sure? Yeah. That's the spirit. It's almost 11 o'clock. I mean, come on. What else would you be doing Saturday morning? You what? Hang out with me? Eh? See, that's the option. Laundry day? I find it much more interesting in life if you have no laundry day. I remember those, you guys were bugging me with the bug problem, so here is something similar. It says minimum distance. Find the point P on line y equals 3x. That is closest to the point 50, 0. Now this problem should make sense as soon as you draw. Say this is your 3x, and here's 50, 0. So what's the distance? Now observe, we don't know where this x and y mysterious point P is. This is the distance, which needs to be minimum. But see, that point could be here, could be here. We really don't know until we do some calculus. So do some calculus. what are we using? What are we minimizing? Distance formula from algebra class. My answer is no. Answer for what? Oh, haven't done it yet. You got it?
No, no, the equation.
The rule from alpha got it? Okay.
Did it without.
Let's take a look at this together and then hit the brake. Distance formula, square root of, so this is 50, 0, right? So it's x minus 50 squared plus y minus 0 squared, and we want to minimize this. We also know that y is equal to 3x, and that is your constraint equation, which you will plug inside when you expand. So x minus 50, we have x squared minus 100x plus 25, two zeros, plus, instead of y, we have 3x. When you square that, you get 9x squared. And all of this under the square root is equal to minimum. So 10x squared minus 100x plus 2500, the square root of that is equal to a minimum. We are going to differentiate this and solve it. Remember, the square root is always 1 over 2 times the square root, and then times the derivative, because it's a chain rule, right, times the derivative of inside the square root, which is 20x minus 100, equals to a 0. Observe that I didn't, yes?
Can we put square on both sides before it's I mean, that's the minimum number, right? So, even if you square it,
Yeah, it should be good. Because technically what you have is the, see, 2 times square root is going to go away, because when you cross multiply into 0,
yeah,
it's still quick.
that would be easier.
Yeah. Well, do it. So x is 50. And now we have to find y. Y is equal to 3x 150. So the point is at 50, 150. Oh no, it's not, it's 5. So 15. Lost my zeros. So 5, 15. That's the point. Let me just. I'll fix this by the end of the day. It's okay. I got 3 out of 3. So the point 5, 15 is the closest to point 50, 0. And that's it. So you will always have constraint equation and objective equation. Objective equation is the one that you will be differentiating. You plug constraint equation into objective equation to reduce the number of variables down to 1, and then you differentiate. There are variations of these problems in textbook. So try for a bunch of these. That's it. So let's have a break. After the break, we are going to take care of 2 sections. One is a bit longer. The first one is longer on differentials and linear approximations. And the second one is very short. After that, so I'll just restart the stream for those. We'll continue